This is a short video introducing our ICCV accepted paper, Resolving Token Space Gradient Conflict, Token Space Manipulation for Transformer-Based Multitask Learning. Let me begin with the core question that motivates our work. When training many tasks together, gradients from different tasks often disagree. Do we always need to eliminate these gradient conflicts to avoid negative transfer, or could some conflicts actually help generalization? And if we do choose to reduce conflict, how can we do that without blowing up parameters or computational cost? Today I will show why the usual intuition conflict equals gradient conflict equals bad is incomplete, and how fire solutions handle conflict, and where they struggle. Then I will review the right way direction our paper takes. Traditionally, optimization-oriented multitask learning treats gradient conflict, for example negative cosine similarity between task gradients, as a driver of negative transfer. A large body of work tries to message gradients so they stop fighting one another, often by projecting or reweighting the updates for shared parameters. You might know representative method in this family such as gradient surgery or loss rebalancing, but there is a more nuanced picture. Not all parameter space conflicts lead to negative transfer, and some can even be beneficial for generalization depending on task relations and how you evaluate the target objective. For instance, Folkmarsh revisits the standard assumption and shows that conflict strength alone is not reliably correlated with negative transfer. The figure and the corresponding explanation on this slide are taken from that study. The takeaway for us is important. When we looked across these results, parameter space gradient conflict does not automatically imply negative transfer. That means randomly deriving conflict to zero is not guaranteed path to better multitask performance. Let's look at a prior approach aimed at fixing conflicts. Recon's strategy is to duplicate entire backbone layers per task when conflicts are detected, essentially turning shared layers into task-specific copies. This can tame conflicts in the parameter space, but at a steeper cost. Parameters and GPU memory grow quickly, especially in large backbones. Even smaller local disagreement can trigger whole layer replacement, which adds work and waste computation. In other words, Recon reduced the conflict, but it does so by scaling the model. In our slides, we compare this against lightweight alternatives and observe that simply removing more conflict did not lead to better accuracy. In fact, we saw cases where aggressive conflict suppression correlated with overfitting and weaker task performance, despite looking good on the complex statistic. Prior methods often detect conflicts at the parameter level. Here we operate in token space on the activations. This provides a more fine-grained analysis of where conflicts appear in practice. We then use that map to decide where to intervene without changing the overall architecture. From here on, I will explain our method and result. Our first step is to measure conflicts directly in token space, not in the parameters. This let us see where tasks actually collide inside representation. We then decompose conflicts into two types. If gradients disagree within the token encoding subspace, we call it a log space conflict. If they disagree in direction orthogonal to what the encoder currently represents, we call it null space conflict. This tells us what to fix and where to fix it. To act on that diagnosis, we apply token modulation for row space conflict and token expansion for a null space conflict. Modulation realigns direction where the capacity already exists. Expansion adds a small task-relevant components where the capacity is missing. The two moves are complementary by design. Here are the key results. First, we see consistent improvements on two benchmarks when we apply token modulation and token expansion together. Second, the cost is negligible. The parameter increase stays at or below 0.3%, so the model remains essentially the same size as the shared encoder baseline. Third, the method are complementary. Task modulation relies conflicts within the token encoding subspace, while token expansion adds small components for conflicts outside that subspace. Using both together beats using either alone across all tasks we tested. Next, we rank layers by token space gradient conflict and insert token modulation plus token expansion in the top K layers. With the sum budget of the layers, so this conflict-driven replacement gives the best scores on every task we evaluate. For pair comparison, we also try an equal size random subset. That version improves over the baseline, but it is consistently weaker than targeting the layers with the highest conflicts. Finally, we flip the order and place token modulation versus token expansion in layers with the lowest measured conflict. The gains are small. This pattern confirms the main idea. Our measurement is predictive and expansion is most effective exactly where conflicts are strongest in token space. The takeaway is simple. Measure first, then intervene only where needed to get the most accuracy for the least change. On task economy with 11 tasks and VIT-based backbone, our variant DTME-MTL ranks first among optimization baselines. The method reduced negative transfer and raised the average accuracy by plus 4.67% compared to the framework task baseline. The model size increased only 0.18% additional parameters. The key point is that we reached the top score while keeping the architecture nearly unchanged. That confirms that targeted token space addis can deliver broad gains without heavy duplication and maintain architecture with proves broad adaptability. Although token modulation and token expansion operates on a token feature rather than weights, we still see an impact on parameter space gradient during training. We track the angle between task gradient as shared parameters and summarize them as histogram over layers and steps. With token modulation and token expansion, the histograms shift away from negative angles and place more mass near zero or positive values. On the conflict metric alone, Recon looks strong because it pushed the negative cosine function even lower. The trade-off is that it duplicates entire blocks for tasks, so parameters and GPU memory grow quickly. In other words, especially on large backbones, that extra capacity overfit the training signals and reduce arbitrary task accuracy compared to wider baselines. By contrast, token modulation and token expansion shifts the gradient angle distribution enough to help optimization, and it does so without duplicating layers. The result is higher accuracy at less than 0.3% extra parameters. Thank you for listening. Full details are in the paper and code, and I'm happy to chat after the talk or by email.